So today we'll be talking about momentum. It's a concept in physics, and so the first thing is, what is momentum? It can be defined as how hard it is to stop an object in motion. An important thing is that momentum is a vector, and so direction is really important when you're dealing with it, and that's something we'll discuss later regarding impulses. There are two kinds of momentum, linear or angular, but first we'll be talking about linear momentum because angular momentum is analogous, and so yeah, that takes us to our formula.
Continue.
So linear momentum is denoted as p and is equivalent to mass times velocity. One interesting concept or idea is that momentum is related to force. So in this image you have two equations. On the left you have the equation for force. F net is equal to mass times acceleration. Well, what do we know about acceleration? It's the instantaneous velocity with respect to time. And so you're going to substitute that derivation into A, and then so you come to F net is equal to mass times dv dt. Well, now let's take a look at momentum. Momentum is equal to mass times velocity. And so what we'll do next is take the derivative of both sides, which gives us dp dt is equal to m times dv dt. Here mass is a constant, and what do you know? The derivations that we just came to are the same. So you could say by using transitive property, F net is equal to dp dt. And that's a big idea which will lead us to another concept regarding momentum. The next idea that we're going to explain will be introduced by the batting of an object. Here in this clip we see a collision. But more importantly, we're going to discuss impulse, or the impact. Surely before impact, the colliding object has momentum. After impact, it also has momentum. However, its final direction is in the opposite direction, and so this impulse is defined as the change in momentum. Here in the left image, we have one of the formulas that we just talked about. Impulse, denoted as J, is the change in momentum. And so we're going to go back to our big idea that dp dt is equal to F net. And so impulse is also related to force by this way. Multiply both sides by dt and you're left with dp is equal to F times dt. And so if you integrate both sides from an initial point in time to a final point in time, you get change in momentum, or J, or impulse, is equal to the average force times delta t. And in this right image, we see a graph in which the x-axis is labeled by time and the y-axis is labeled by the force. And so basically we just integrated, and so the concept of integration is the area under the curve. And so this is another way to find impulse, by taking the area under the curve of a force times time graph. So the next concept that we're going to talk about is the conservation of momentum. So remember our big idea that F net is equal to dp dt, and so let's set that to 0, or let's set our F net to 0, which means that our net external forces acting on the object are 0. And so if we integrate, we basically get that the change in momentum is constant. And so does that sound familiar? Yes, it does. It means conservation. And so this only happens under certain conditions. And first, the system must be isolated, that's number one. And second, the net external forces must sum up to 0. And so because momentum is conserved, that brings us to our universal equation, that the initial momenta of two objects will be the same as the final momenta of two objects, or m1v1 plus m2v2 is equal to m1v1f plus m2v2f. And that is our concept of conservation of momentum. So in an elastic collision, kinetic energy is conserved, but that's not to be confused with E mechanical. And lastly, momentum is conserved in an elastic collision. And next we have an inelastic collision. And you'll notice that the colliding objects become one upon impact, but it is important to note that unlike in elastic collision, kinetic energy in an inelastic collision is not conserved. Instead, it is lost as either thermal energy or heat, or potential energy, or the energy of sound. Momentum is definitely conserved, and so that brings us to our equation for an inelastic collision, which states that m1v1i plus m2v2i is equal to quantity m1 plus m2 times vf. Okay, so we won't be going into too much detail regarding angular momentum because, hey, no one likes rotation and it's really difficult to understand, but we will start off with the fact that it is analogous to linear momentum. And so angular momentum is denoted as L, which is analogous to our P, linear momentum, and it's equal to rotational inertia times angular velocity. And the angular equivalent of our big idea would be torque. Net torque is equal to dl dt. And so angular momentum is especially important because it involves momentum of a rotating rigid body around a fixed axis and is also conserved unless an external torque acts on it. Okay, so a quick tip when solving problems involving momentum is that you may come across a problem in which the object is colliding in two-dimensional motion. And so in this case you would have to take the respective components of the objects colliding. And so of course for the vertical component you would use the sine of an angle, and for the horizontal component you would use the cosine of an angle. Another important idea that relates to momentum is relativity. You may come across a problem in which the two colliding objects' velocities are not given with respect to a single frame, but to each other instead. The problem might also ask that you determine the final or initial speed with respect to a single particular frame or reference frame. And so the problem might involve, let's say, a spaceship ejecting a module. So the easiest way to understand relativity may be through this picture that we found in our textbook. And so the book explains this as Alex, who is denoted as being a part of frame A, while Barbara, making her own frame, is mobile and constant velocity. The two are both watching particle P, which is also in motion. If you take a look at the position of particle P with respect to frame A, it is the sum of the position of particle P relative to frame B and the position of B relative to frame A. And so next you're going to derive this formula, and you get the velocity of P with relative to frame A is equal to the sum of the velocity of P relative to frame B and the velocity of B relative to frame A. But this only works if the frames move at constant velocity, so that is one thing to look out for.